We are live.
Hello, everyone, and welcome to the second session on the third day of QMAT 2021. I will hand it over to our session chair, Sunil Nair. But before that, a couple of announcements. The long talks are 25 minutes plus 5 minutes question and answer. Question and answer should be kept for the end of the talk and not in the middle of the talk. If you have a very pressing question in the middle of the talk, type it in the chat and the chair will take it up at the end of the talk. If you are having an argument and that cannot be resolved within a reasonable time, we will have some breakout rooms in this session, and you can go with the speaker to the breakout room to settle those issues while the program can continue uninterrupted here. Okay. And with that, I would just hand it over to our chair, Professor Sunil Nair from NISER, Pune. Sunil.
Thank you, Rajdeep, for that. So good morning, everyone. So let us, without any further ado, go on to the first speaker of the session, Dr. Debashish Banerjee from SINP. And Debashish, so you can start sharing your slide, and I'll give you a shout exactly at 20 minutes, so you know that you have to wind up in 5 more minutes.
Debashish, you're
Thanks. Yeah, I had to unmute it. Sorry. Okay. Thanks a lot for the introduction, and I hope I'm audible. So I would like to begin by thanking the organizers for the opportunity to present this work on this very nice national conference. And today I'll talk to you about the investigation of potential bosonic and fermionic liquid-like phases from gauge theories. And this is a topic that's I think of equal interest, not only in the quantum condensed matter community, but also from the high energy lattice gauge theory community. So this makes for a lot of interdisciplinary discussion, which I like a lot. Right. So this work is done in collaboration with Emily Huffman and Lucas Müller, and we hope to be finished with this work hopefully soon. The outline of the talk is as follows. So first, I will motivate the approach of using gauge theories in order to, or other microscopic gauge theories in order to analyze the phases of potential spin liquids. And then I'll tell you a bit about what are the microscopic models that I have in mind, and why we find this interesting, and hopefully why you should also find this interesting. I will also then discuss the features of these models in 2 and then in 3 spatial dimensions, and then I'll give you some results, almost always in 3 spatial dimensions, even though the lattices are very small. I would then conclude with an outlook. Right? So here comes the motivation. So I hardly need to emphasize, at least to this audience, the important role that emergent gauge theories play in describing a host of phases in condensed matter physics. However, just to spell it out, the example that I have in mind is that of the low energy physics of frustrated antiferromagnets, right? And as you all know, that these are substances these are phases that would happen in naturally occurring substances such as water ice, or in the pyrochlore materials, right? So we had a very nice talk about this holmium titanate, the physics in the holmium titanate compound on Wednesday. Ready? So the idea is, of course, very simple. Is that if you take so these models have very strong geometrical constraints, as a result of which, if you go to very low temperatures, you see that there's not one, but there's a very large number of classical configurations which satisfy these constraints, right? These are called so-called the ice states. And the most quintessential example is that if you take these Ising spins, couple them antiferromagnetically and place them on a tetrahedron, you see that there are not one, but actually 6 such configurations. And now you want to include quantum mechanics into the game. So you need to have operators in your effective Hamiltonian, which cause tunneling between these one ice state to the other. And you need operators like this, the loop operators like this, as shown in red. And it turns out that these loop operators are exactly the ones which are gauge invariant, right? And therefore, it's not a surprise that these low energy spin liquid phases, which are conjectured to exist in these models, admit a gauge theory description, right? So what I'm going to do is that I'm going to use microscopically gauge invariant models to address the phases, right? So these models will not, the gauge invariance is built in them already. So it's not that gauge theory will emerge, but rather it's built in. And because it's built in, I have luxury to choose what kind of gauge invariance I want, and if I want any matter fields or not, and so on, right? And for the purposes of this talk, I will exclusively be concerned with the pure abelian U1 lattice gauge theory, right? And I will not have any matter anywhere, right? And whenever you want to, understand these gauge theories, it's nice to look at the very beginning in the works of Wilson, Kogut, and Susskind, who realized these abelian gauge theories by using quantum rotors at degrees of freedom. So these degrees of freedom, they live on the links between the sites, and the electric flux is identified with the z component of the angular momentum, and the gauge fields are just the raising and the lowering operators, right? And because they're canonically conjugate operators, they satisfy the following commutation relations, right? So now you can go ahead and write down the Hamiltonian, which simply comprises of this electric flux term, this electric energy term E squared, and the magnetic energy term, which is just the plaquette and the plaquette dagger, right? And the plaquette dagger is just, the plaquette is just simply the closed loop of the gauge fields that you can write down, which in the context of this hypercubic lattice or square lattice, depending on which dimension you're working in, you just have a 4-body term, right? This U dagger, and U dagger. This is the magnetic energy term. Now, the gauge invariance of this Hamiltonian is also very easy to see. Actually, it was nicely explained by Indrajit in the talk in the last session. You can write down a local operator, which is the Gauss law, right, at every vertex. And this vertex and this operator is just the lattice divergence of the electric flux, right? So there are in three dimensions, you have three links touching a site, pointing in the forward direction, and 3 links in the backward direction. So you just have to take the lattice divergence appropriately. And you can very easily show that this commutes with the Hamiltonian, right? So this accounts for the local invariance, and you can define the unitary transformation and show the invariance and so on. Now, when I talk about the quantum link models, what I have in mind is slightly a more general class of theories that was introduced by Wilson. So instead of the quantum rotor, which you had, now you have quantum spins, right? So quantum spins means that you have a finite dimensional Hilbert space 2s plus 1, and you proceed along the same way. You identify the electric flux with the z component of the quantum spin, and the raising and the lowering operators are the gauge fields U and U dagger, right? And notice that the commutation relations which we introduced in the slide before, which were necessary to have gauge invariance, are the same. So EU, so S plus, so SZ and S plus will give you an S plus, and so on. So this means that the gauge structure of the theory is intact, right? And therefore, you can write down the Gauss law, the Hamiltonian, exactly in terms of the same operators that you had before. The only difference is that the Hilbert space is changed now, right? So these operators now act on a different Hilbert space. That's the main difference. And the other thing is that your U and U dagger are no longer commute. And these two things, result in the fact that the physics that you see in these models are actually much richer than the Wilson-type theories. And just a historical note, it's just that these models are not new. They have been investigated by a lot of people, over the decades, right? The names are here. In any case, so the models I would be concerned with in this talk would work with the minimal spin half representation, right? So you would have a spin half. Also very much like Indrajit did in his talk in the last session. So you have a 2-dimensional Hilbert space. So the electric flux only gives you a plus half and a minus half, depending on acting on the 2 states, and you have the gauge operators doing their raising and lowering jobs, right? That's pretty simple to imagine. Now you might ask, what help did it work with with these new generalized lattice gauge theories? It turns out that you have a lot of new phases. You have various anomalous thermalization physics in these models due to the presence of stars. Then you can have fragmentation. You have possibilities of quantum simulation, and so on, right? And so some of these have already been discussed in the seminars, in the talks in this conference. I will not go into it, but I will go on to push ahead to generalizing these constructions even further, right? So take for example the case of the spin half case. You have a two-dimensional Hilbert space already at every link. But now the question I want to ask is that is it possible to generalize this construction even further? And what I have in mind is the use of fermions, right? So what I'll do is that the two-dimensional Hilbert space, right, I will exhaust by two states by saying that either the fermion is present, that corresponds to one state, or the fermion is absent, that corresponds to the other state. And now if I want to, write down my corresponding gauge operators and electric flux operators, I will proceed in the following way. And so the creation operator for fermion, right? So this acts as the U operator. The U dagger is the annihilation operator for the fermion. The electric flux is simply the number operator minus a half. And you need this half for aesthetic reasons because n is equal to 0s and 1. And, the spin, you have plus half and minus half. So this provides a one-to-one map between the two. Now, written in this way, remember the plaquette operator was a 4-body operator, right? We had like a U dagger. And with this identification, you see that this corresponds of two creation operators and two annihilation operators, right? And as we will see in the next slide, this corresponds to a correlated hop, right? But it's easy to think a bit further. You have the Gauss law, which was a divergence of the electric fluxes, remember, and this in this identification turns out to be a divergence of the occupation number on the links. The forward pointing links minus the occupation number in the backward pointing links. Okay? And again, with whatever I said before, it's very easy to motivate that this construction will work because the commutation relations that are satisfied with by the number operator and the C and the C dagger operators are exactly the same ones which the U and the E were satisfying to have the gauge invariance, right? And therefore this construction works. However, is anything new? The answer is yes, there's something new because now, as you all know, the fermions anti-commute, right? Which the spins did not do. So therefore, in large enough spatial dimensions, you do expect that the motion of the fermions could give rise to interesting physics. Right? Now, what about this plaquette operator that I was talking to you about? How do I imagine this? This is the most non-trivial operator to imagine. And since it's a two-body operator, it always causes two fermions to hop, right, on a single plaquette. And of course, if you need to have two hoppings, simultaneous hoppings, correlated hoppings all in one go, you must have two occupied sites and two empty sites, right? Otherwise, both hoppings cannot occur. And this would naively give rise to 6 possibilities. But it turns out that because of the gauge invariance, right, only 2 of these hoppings are actually allowed. And these 2 hoppings correspond to when these 2 sites are filled and these 2 sites are empty. So the fermions are hopping, in this direction. Or if these 2 sites are filled and these 2 sites are empty, then the fermions can hop in the other direction. Right? So that's all about it. Now you can go ahead and write down all these, all the internal symmetries. You can write down charge configuration, you can write down parity, and you can also write down the lattice point group symmetries, like the translations, the rotations, and so on. And the models that we construct are all invariant under these symmetries. Right? Moreover, it's also possible to write down these global winding number symmetries. Occur in these kind of lattice gauge theories. I have sketched 2 configurations here corresponding to the various occupation numbers of the fermions. So the one on the left has a 0 winding in pi, and the second one has a maximal maximal winding for this particular lattice, right? So all this can be done in 3 spatial dimensions as well, or in any spatial dimension. Okay. So now the question we want to ask is that, okay, so one more thing I should emphasize is that what about the Gauss law now? So in 2 dimensions, also if you were in Indogeek's talk, he explained that there are 6 such configurations which satisfy the Gauss law equal to 0 constraint. In 3 dimensions, there are many more, and it turned out if you count them, there are 20 such configurations, right, at a single site. Okay, so now that we have defined these models also with using fermions, the question we want to ask is that is the physics any different, right, with these fermionic models? So first we ask the question in 2 spatial dimensions because we have studied the corresponding spin model in 2 spatial dimensions extremely well, right? We know both the static and the dynamic properties of the system, and we just want to understand if realizing them as fermionic operators make any difference, right? The answer is no. And in these pictures, I have given I've outlined a geometrical proof of the statement, which I will not go in detail in view of the time. But what I want to point out is that once you impose this gauge invariance condition, the only hops, right, that are allowed make the fermions move along these diagonal lines that I have drawn, right? So, for example, if you look at this, the top left figure, you have two fermions whose position, which I've sketched in red, and the rest of them are in blue. You can try to hop these fermions as much as you want, but you'll never be able to flip their positions, with respect to one another, and keeping everything else in the background fixed. So what does this mean? This means that the fermionic word lines, which would be the matrix elements of the Hamiltonian, which could have potentially given a negative sign, right? As opposed to the bosonic, or the one with the spins, do not arise here anymore, right? Because the fermions cannot really interchange their positions, right? Because of the gauge invariance, such swap is forbidden, and therefore, in short, the fermions are constrained to move along one of the overlapping planes. Right, and it turns out that if you look at the spectra, they're identically the same with that of the bosonic model, as expected also from this proof. So the physics in two spatial dimension is identical to the spin half quantum length model, right? So this is a nice geometric argument coming out. Also a bit disappointing because you see that, well, there are no new physics perhaps, but there's nothing to despair. You can climb in one spatial dimension higher, and there you can show that you indeed have different physics. Right? So here what happens is that if you try to extend the geometric proof, which I was outlining before, you will realize the fermions now in this case move along planes, right? So for example, these two colored fermions, for example, they will move along planes that I'm trying to indicate with these particular arrows. And when the fermions move in planes, it's highly possible for the two fermions, as I've shown in this figure 1, 2, and 3, to change their respective orientations, right, without affecting any other fermion in this configuration. And therefore, those matrix elements, which would have given a negative sign, in contrast to the spin version, are there. They contribute very well. In the language of quantum Monte Carlo, you would say the fermion word lines contribute very much. And so there are negative signs, and then the model built with fermions are expected to be qualitatively different, right? So how do we do this? How do we verify the physics? We don't at the moment have any efficient Monte Carlo algorithm. So we do exact diagonalization up to whatever modest lattices that we have in sizes we have in reach. And the exact Hamiltonian that we take are the following. So we have this is the magnetic term. You have the fermions hopping. You can think of this as a kinetic term, which makes these fermions hop, right? They hop from here to here, and then you have this lambda term, very much similar to the Rothschild-Wilson. In fact, it is the Rothschild-Wilson term. This counts the number of plaquettes which can potentially be flippable, right? So you see, this is a flippable plaquette because this jump is allowed. So it's exactly the same model that, for example, Indrajit was also talking about for reference, but this is just in 3 dimensions and realized with fermions. Right. So what I will talk next is about the results, and for the results I'll be always comparing 2 different models, right? So one model in 3 dimensions is the model realized with spins, right, which is what we call bosons. So you could also have given a hardcore boson representation to the spins. That's why I call them bosons. And then you have the other model which compose of fermions as the basic degrees of freedom, right? Diagram to be based on results we have from our exact diagonalization data. So for very large and negative lambda, what you expect is that this particular term is expected to dominate. Let's look at this term, right? This term dominates when lambda is large and negative, obviously, and this term kind of prohibits scaling, prohibits fermions from jumping, right? It kind of, you can think of it like a potential term which counts how many number of flippable plaquettes there are, right? So if it is the counting term, it does not allow the fermions to jump, and therefore you would expect that in this limit, the physics of the bosonic and the fermionic would be similar. Right, and it is indeed the case, and as we will show that there is a particular rotation symmetry that is broken, spontaneously broken in this limit, and giving rise to some nematic order. Now, what happens is that as you keep decreasing lambda, right, then the fermion hoppings are more encouraged. simply because lambda goes down, and the J term, which would have, the kinetic term, which would flip these plaquettes and make the fermions hop around all over the lattice, that is highly encouraged in comparison to the potential term, and therefore, because of this motion, you seem to come out of a nematic ordered phase. So the nematic order seems to dissolve, right? So this is a better way of making the statement than saying that we see a quantum spin liquid, right? So we see that the order that we have dissolves, and we do not see the formation of any other order, right, in this region. That's, I think, the more honest way of stating the results. And then, of course, as you increase lambda, we all know that at lambda equal to 1, this is this so-called Rothschild-Wilson point, which I think is extremely well known in the condensed matter community. So you also come to this point. In the bosonic model, smoothly connected with this liquid-like phase, right? However, in the fermionic model, there is a surprise. There's this very narrow region, well, not so narrow on small lattices, where you see a phase where the flux tubes seem to condense. So in some sense, it's similar to the staggered phase that one has beyond lambda equal to 1, but it's also different from the staggered phase in certain respects, right? So we don't fully understand the nature of this phase as of now. Now, of course, this is not the first time we are saying any of this. This has been extensively investigated in the literature. There are many, many papers. But let me just point out the two papers which I think are most similar to the model that we are talking about. So this one is the work by Kedar and collaborators about the hardcore bosons and the pyrochlore, which was investigated with a quantum Monte Carlo algorithm. And then there was a work by Nick Shannon, Frank Coleman, Carlo Peng, Peter Fulde, where they looked at the quantum diamond model on the diamond lattice, right? And in both these works reported the presence of these liquid-like phases, right, using various observables.
Debashish, so also around 5 minutes more.
Okay, yes, good. All right. So I'll just outline the results now. So of course we are, we are using exact diagonalization. So clearly we are only limited in lattice size. So we could only do 2 cross 2 cross 2, 2 cross 2 cross 4, and 2 cross 2 cross 6. And already you see the number of lattice links is like 48 and 72 for the largest lattices. This corresponds to like 10 to the power 10 states that you have, to do with your Longshore diagonalization. So this is already the limit, what one can do. Anyway, so what I'm showing you here in this figure on the x-axis is the lambda, and on the y-axis is the mass gap, right, from the ground state with the lowest 50 excited states. Right? And then at larger lambda, you see that the bosonic and the fermionic spectra are very similar. They are very close to 0. The gaps are very close to 0, which is consistent with the fact that there's a spontaneous symmetry breaking in this region. Now, as you decrease lambda to 0, you see that this gap, this tiny gap goes away, and then you come to this area in lambda, which is lambda close to 0, which is a highly messy area, right? So you see that there are lots of these excited states which are also coming down. There are a bunch of level crossings happening over here, right? And we will investigate this area in a much more detail. But let me already point out that you see this particular state that is coming down, and this state is a state with a flux, right? So at lambda equal to 0 in the bosonic model, what you would say is that it is easier to excite a flux excitation than to excite the next excitation in a zero flux sector, right? This is something to be kept in mind. In the fermionic model, of course, there are different level crossings leading to the idea that the phase realized here is qualitatively different from the one realized with the bosons, right? So let's see how the scaling works in the nematic phase. This is the one that is easiest to explain. By looking at the symmetries, you can easily figure out there is this dihedral group, this D3 cross Z2 symmetry, which is continuously broken. So D3 is the rotational symmetry, Z2 is the charge conjugation, and this predicts that there will be 12 states which are degenerate in the thermodynamic limit. And here, what I'm showing you is this is a mass gap for 24, 48, and 72 links, and then you see the exponential decay as expected. The y-axis is on exponential scale, right? And you also see the particular degeneracies, right? This 1 plus 2 plus 3 plus 3 plus 2 plus 1, which is very characteristic of this particular group, which is a non-abelian group. Now, what happens if you come out of the nematic phase? So here we are comparing the mass gap in the zero flux sector, right? So there's no flux. We've restricted ourselves to 0, 0, 0. We look at the gap at -3 and compare it with the gap at lambda equal to 0. With lambda equal to -3, you see that, this again the same exponential scaling as we saw before. Now you're wondering what these numbers are. So this is related to some technical computation that we have done. So for the moment, you should ignore the numbers and just look at the point with the darkest shade. In other words, just look at the one with the highest number, right? So in this case, you see, so this is somehow indicative of how fast we converge to our results for the largest lattice. Now at lambda equal to 0, you see that the scaling of the gap is much less stronger, right? So this strong exponential gap has kind of almost disappeared. You could argue that there's a very weak exponential gap, or you could also argue that there's a power law gap. It's impossible to say with these small lattices. So that's a big caveat of the story that I'm telling. And I would just like to point out that at lambda equal to 0, flux strings are also very easy to excite, right? Which is very different from a confined model, which for example you would see in 2 spatial dimensions, right? So again, you see something similar in the fermionic case. You have a very strongly scaling gap at lambda equal to -3, but you have a gap which scales less weakly at lambda equal to 0, right? So at least one tends to think that the nematic order is slowly melting. Now, actually, to identify this a bit better, we have what we call the state participation histogram, and then I think I will stop after describing this. So what I'm looking at is on the x-axis, I'm plotting the log of the overlap of these basis state with the ground state, right? So this is what I have in mind. This is the x-axis, the log of this overlap, and on the y-axis, you are plotting how many states come here. Right? So you see at lambda equal to 0, which is indicated by this red, you see that at lambda equal to -3, there's a lot of weight, right, given to only a very few configurations, which indicates the symmetry breaking. But at lambda equal to 0, that entirely disappears, and you have this blue histogram, which does not indicate any particular scale in the ground state wave function, right? Almost all these states seem to contribute, right, and there's no one particular thing that you can separate out. And notice that this is a log scale, right, the x-axis, which kind of makes a very compelling argument that all these states are kind of centered around a particular line. Now, I think I'm kind of almost over my time. Is that right, Sunil?
Yes, that's right.
Okay, good. So I will just leave these things open, that we've also studied a bit of several other observables as well. And we think that we do see the melting of an ordered phase, definitely, and we do not see the emergence of any other ordered phase, right? So it leads us to think that we would have a liquid phase at lambda equal to 0. There are several other interesting research directions in this area, and at this point, I think I would like to stop. And yeah.
Thank you very much, Debashish. We have probably just time for 1 or 2 short questions. So I can see that Arnab Sen has raised his hand. Arnab, could you please go ahead and ask a question?
Yeah, sure. So Debashish, I had just one question. So in this fermionic model, when you see this quantum spill liquid, at least from the ET, it didn't seem very dissimilar to the bosonic one. But then in a fermionic theory, it's hard to imagine how you would form this photon, which is very characteristic of the bosonic theory. So do you have some comments on that?
Yes. Actually, no. So this is one of the big question marks I have. How do you form a low energy effective theory of the Coulomb phase with fermionic gauge fields? So this is something I'm thinking about. I don't have any answer to that.
I see. But numerically, they seem similar to each other. Is that correct?
Yeah, they do. But there are also some glaring differences. Like in the fermionic case, you see that here there are a lot of these states, right, which are all have 0 weight. They were contributing to the bosonic model, but they do not contribute in the fermionic model at all. So a large part of the weight gets shifted in the the very late, which is due to the cancellations that are occurring. And so we think that it's similar, but not, of course, exactly the same.
Okay, thanks.
Maybe one last question, if someone has something really pressing to ask. Feel free to raise your hand and go ahead and ask it. Okay, doesn't seem to be the case. In that case, let me take the opportunity to thank Debashish for his talk. Thank you very much, Debashish. And
thank you for listening. Yeah.
You can share your slides, and we can move on to the next speaker, who is Dr. Sudeshna Sen from IIT Dhanbad, who will be talking about the theory of benzene transistor, symmetry, strong correlations, and quantum interference. Sudeshna, could you please?
Yes, so is my
So
screen
please go ahead. I will give you a shout exactly at 20 minutes so that you can wrap up the next part.
Yeah, okay, thank you. Okay, so before I begin, I would like to thank the organizers for organizing such a wonderful event. And yeah, so in the next 20 or so minutes, I'll walk you through a story of a molecular transistor. So we'll dive into the realm of molecular electronics. And, as the title suggests, the main players of the story will be symmetry of the molecule that's involved in this conduction of electrons or in the transistor, and the interactions present on the electrons that are moving across the leads through the molecule, and the interference because of the orbital complexity of this molecule. Before beginning with the main part of the talk, this work was initiated while I was a postdoc in Ireland, so in University College Dublin. So I would like to thank the funding that I had received from there, and it's being continued here in my current institute. So I would also like to thank my current institute for funding it. And this work is done in collaboration with two excellent students from the previous group and Professor Andrew Mitchell, so I acknowledge them. So, just to give you a backdrop, I know this audience does not need that introduction, but to give you a backdrop and motivate you. Basically, I'll talk about the miniaturization when, in the nanoscale limit. So if you look at this figure over here, we are already in this limit of the order of, something say 50 nanometers. And these are all, using silicon microprocessors, but I'm asking that what if we go down further? And you might ask that why do we need to go down further? That's a valid question, but as I hope that as I go through the talk, you will realize that it's not a bad idea to go down further, because you get to know a lot more, even from the fundamental physics level. And to motivate you further, actually, there had been recently, developments in this direction where single molecules have been integrated in CMOS chips and have been used in medical applications. So what is the regime, or what is the length scale I'm going to talk about? I will be in this regime, and nature provides us with an enormous number of such molecules at hand, which we can utilize in this regime for certain physics that we want to look into. And why we would want to look into that? Because this is a regime where it's purely quantum in nature, and it's quantum nature of correlations with no classical analog. You can manipulate the interactions of the strong electron correlations, Coulomb correlations present on these molecules, and they hybridize with the electrodes, and in the process you can control that hybridization. So you have control in it, and there has been a lot of advancement in on the experimental side. Experimental challenges are enormous in nature, but there has been advancement, and this can be done, as was shown way back in 2008, where they had shown that indeed, if I can manipulate these couplings over here, I can really manipulate the conduction of that channel of the transistor. So these can be done. And it's not just that, as you will see, you can also predict a lot more. So a typical single molecule junction would have the structure is like this, where you have a molecule in the middle, which acts like a channel for the electrons to pass through from one side to the other. So these are, let's say, the leads, which are made of good metals like gold or platinum. So these are the leads, and this is the channel, and this is basically the molecule. And what I have done is chosen a very simple molecule, which is, let's say, just this ring over here, which is a six site ring, the simplest molecule with enough complications in it so that the theory can be developed for further developments. Okay, so the current through this channel it can be tuned by this bias voltage, as you know, and what one measures in the experiment is the conductance, which is the dIdV curves. And additionally, you can tune the number of electrons present in this channel. So you can, or the number of electrons that you want on this molecule, and that, or the on-site potential of this molecule over here, and that is tuned by a gate voltage. And in the mathematical Hamiltonian language, you can write this in this form, where n mole is the number of molecules present here, and that tunes the energy levels, basically the ground state energy level. So why would we want it? Again, quantum boosted functionality, because so there are three. So in this slide, I have like three pictures over here. Okay, so let me take you through that. So let's say I have this benzene ring. As you will see, this benzene ring, depending on the filling, can have an unpaired electron. And depending on the temperature, that unpaired electron can be seen by these electrons, these 10 to the power 23 number of electrons on each of these leads, as a single molecular moment, and they behave in a particular way, and that's Kondo effect. And that behavior is purely because of Coulomb interaction, that arises because of Coulomb interactions as you go down in temperature. So that's one effect that will definitely happen in these systems. Additionally, there are orbital complexities in these molecules, and different molecules that we have in the nature has different kind of orbital structure, and depending on the orbital structure, and as I said, there is this hybridization, and depending on how these orbitals hybridize with the leads, the electrons may get hindrance or may easily pass through the channel and things like that, and that leads to something that is called interference. And that quantum interference involving these electron wave functions, or the orbitals, that manifest as nodes in the conductance curve. So these are nodes or resonances actually. So that interference is also another aspect that is present. But now I ask, what happens if you combine this interference because of the orbital complexity and the Kondo effect, and additionally you put in symmetry. So for example, this 6-side ring, as you can see, it's easy to visualize that depending on where I connect the two leads, my symmetry of this whole junction will be different. And this symmetry will manifest in the orbital wave functions of this isolated system. And as you'll see, that will determine certain features of this entire junction and can give completely different physics and completely different functionalities. And for example, you can get a quantum phase transition. So then how does it help? I mean, how does it boost my functionality? So I can now tune my system, my transistor, close to a quantum phase transition. And in the process, I can get very fast electronics. And again, these are robust processes that will always happen below a certain temperature scale. So you are guaranteed to get that effect. It will be low power because it's close to a quantum phase transition. So the sensitivity is enormous. So in that sense, you'll get enhanced sensors. And the third thing is, now we have a plethora of such molecules, so which we can control. Until now, we utilize, so in silicon microprocessors, we utilize quantum effects, but we don't really have a lot of control in them. But now you have such a lot of choice that you can control those quantum functionalities, and that might in the long run might be useful for the next generation revolution, where you can really control those functionalities. And these benzene-based single molecule junctions are not rare. I mean, there had been a lot of work, and it can be synthesized in for tabletop experiments. So these are a few, this slide is a few collage of few of these references, and there are a lot more. And I'm definitely not doing justice, but by not citing, but there are a lot more. Okay. So now coming to so I think I have motivated you enough, and now how do you model such junctions? So again, so schematically, you have a molecule over here, you have the 2 electrodes, and you have a gate voltage through which what you can do is this molecule will have these discrete energy levels, and by tuning the number of electrons over here, you can tune the ground state of your system. And depending on how close your state, low-lying state, the ground state is, the level that is close to the Fermi level, how close it is, depending on that, an electron can tunnel. So that's one way of tunneling the electrons across the junction. But what I will talk about is a different regime. And again, before I talk about that different regime, what you can have is there could be some charging energy. So in the classical, you can not classical limit in the sense that there could be a charging energy cost, and depending on whether the electron really wants to pay that charging energy or not, depending on the filling, you might have a suppression of conductance, and the electron would not want to move. Electron will only move if you allow that electron number occupancy of, to be the ground state. I mean, this picture will be clear in the next slide. But there is another way which is not confined to this, to this just the ground state energy level of the molecule. There is another way in which there can be conduction, as I was talking about, and that's through the Coulomb interactions and the Kondo effect. So now what can happen is, as you can see, so let's say I have in this picture, I have, let's say, this residual, so a free magnetic moment, a free spin. Okay, the filling is such that of the molecule, the filling is such that I have a free electron and a free spin sitting on this level, and I have these electrons, of course, in the leads. But now again, so if I want to now conduct current through this channel, I have to make an electron hop from here to here, right? But in the process, I know that I have to pay an energy cost U. But because of Kondo effect, or there could be processes in which there could be these virtual processes which are possible because of if you are at low enough temperatures. So those virtual processes are higher energy excitations, but they are possible. In the process, what happens that one electron then can come and sit over here, which is definitely a higher energy level, of course, for this molecule, but that's allowed. So the electron comes and sits over here. But in the process, what happens is, instead of that, so earlier it was the downspin, but what happens is now the downspin moves ahead into the next lead, and in the process you are left over with an upspin on this molecule. So what happened in this process, because of these virtual scatterings that had happened, is that the spin has flipped. So initially you had a downspin, but now on the molecule you have an upspin. And in the process, you have this antiferromagnetic correlations between the electrons in the lead and this spin, between the spin in the lead and the spin here on this molecule. So that is this picture. So at high enough temperatures, the electrons in the leads just sees this as some scattering center. So you will have normal Fermi liquid-like characteristics here in the conductance, where with increasing temperature the conductance decreases. But as you increase, as you go lower down in temperature, below a certain temperature scale, what you can see is that because these processes become more and more dominant, what happens is you get an enhanced conductance. Okay, where the electrons keep hopping from here to here because of this interaction between this molecular spin and the spin density on the, I would say to be correct, spin density on these electrodes. So that's this enhancement, and this is something that's called the unitarity limit. So that's the technical term. So that's the enhancement of conductance. So in principle, what happens is, as long as you are your molecule has a stable ground state and you are in a fixed electron level, fixed electron state, for example n or n plus 1, n minus 1 or n plus 1, then you will not have, in principle you cannot have any conductance. So these are the Coulomb, known as the Coulomb blockades, and you will have suppressed conductance. Whatever conductance you have is just through tunneling, but you have suppressed conductance. And in principle, the conductance only happens when there is a change in the electron number. So, when it goes from n to n plus 1 or n to n minus 1. However, in the odd electron regime, okay, you can have something called the spin condo effect, where you can see enhancement. So if you go across, if you go up in this direction, you can see a conductance enhancement below a certain temperature scale. So these are the Coulomb blockade wells, but in the spin half condo or in the spin condo regime, you can actually see an enhancement of the conductance. So this is already an example of quantum boosted functionality, where ideally you should have where Coulomb, you can enhance conductance. Okay. So that's what typically happens in these systems. But when I mentioned this modeling, this kind of modeling, the backdrop that I had in mind was, I was only talking about in terms of a single energy level over here. And there's no degeneracy, it's just a single energy level. However, when you give me such complicated molecules, it's quite understandable that it will not just be a single energy level, but it will be a lot of other energy levels, because we know that these systems are complicated, and we'll already be able to see that for this benzene system. So our line of attack then for these kind of general modeling would be where you will not just have this single energy level on the molecule, would be that, let's say I can have some method. We already have first principles methods available that can treat the isolated molecular system and give us an idea about the orbitals present. We can then fit that molecule to some minimal models like the Hubbard model, or there are other extended Hubbard-like models with few active orbitals, which we know that already we'll get that idea from this first principles calculation, few active orbitals which will be involved in the hybridization with the leads here. And then our strategy is, we have already done this, where we have just considered a few active orbitals and not the entire orbital, but this will be enough. And then we'll solve that using some state-of-the-art. We can approach it in two ways. One is completely numerical, using some state-of-the-art numerical solvers. For example, in this work, I have used a numerical renormalization group. And additionally, to get analytical insights, we can also perturbatively map this already minimal model to some effective low energy Hamiltonians by doing some perturbatively projecting out some high energy features of this Hubbard-like model, and then map it onto some low energy model, just to have an idea about the physics that's happening at low energy scales. And we will again always work deep inside a Coulomb diamond. That is, we have a fixed electron number, and that electron number can be tuned by tuning the gate voltage. And just to give you an idea as to what such an effective model Hamiltonian is, for example, for this single level model that single level schematic or system that I was talking about, this could be, that low energy effective Hamiltonian could be this kind of an Anderson impurity model, where you model, I've called this a dot, where the single level, the orbital here, has this kind of a structure where you have some on-site potential energy. So these These are known to us, and this is the interaction energy, where, for example, when the electron was coming and hopping over here, it would have to pay some interaction energy. So that's this thing, and that's necessary for getting the Kondo effect. And then again, the conduction electrons have this general band structure Hamiltonian, and then you have a tunnel coupling, which simulates the hybridization of the orbitals with the leads. And the low energy, so now you can do the perturbative mapping, and you will end up with something like the Kondo model, where, as I said, where in that regime, I can imagine that I have this free spin over here, and I have a spin density from the leads, and they talk to each other, let's say antiferromagnetically or ferromagnetically. I mean, in the Kondo model, it's in the antiferromagnetic interaction. So that's how they couple, and that's the interaction energy through which they talk to each other, through which the leads talk to the molecule. But in reality, this is what it is. We have this several energy levels, and as it will turn out that it will be a generalized Kondo model. So this is not allowed. We'll have something called a generalized Kondo model. And
Sudeshna, you have 5 minutes more.
Yeah, so this is a technical slide. So as I said, you'll have a generalized Kondo model, and then you can go ahead with that generalized Kondo model. So what happens now is that earlier we did not have this J as matrices. They were just a coupling constant, because these, but now, because we had just a single level here. But now, let's say I have this benzene system. What happens is I can individually, I can exactly diagonalize that effective Hamiltonian, Hubbard-like Hamiltonian on the benzene system. And I will see that already for the benzene system, because of the symmetry and the orbital structure, you have, let's say I'm just focusing on the 7 electron state, can tune the filling as I said, but already here, if I focus, this is actually a 4 level degenerate system. So it is not just spin up and down. You additionally have a parity symmetry for these orbitals that you can assign to it. So it's a 4 level system. So which means that, you know, the interaction between the 2 spins has already that structure. So that's what we'll do. So it will not just have this thing, but you'll have other phenomena as well. And because of this 4 level, 4 degenerate levels, it becomes more complex, and you have spin and orbital. So I call this orbital pseudo spin. And because you have, earlier you had for spin the Kondo effect, so that was the Kondo energy scale, but now you have an orbital pseudo spin. So let's say now you will have a pseudo spin energy scale. Okay, so the next 2 minutes, let me just give you a glimpse of the result. Again, in view of time, it's not possible to show all the entire gate voltage range. So I've just chosen this small area, but this itself is so rich. So this is just the n equals to 7. Okay, so you have essentially you have a residual spin half sitting on the 6-site benzene ring, and you have these orbital pseudo spins. And already here, if you can see, so if this is the as a function of temperature, so I go down in temperature. So this is the entropy, which means the effective degrees of freedom as I go down in temperature, how the Hamiltonian behaves, renormalizes as I go down in temperature. So at high enough temperatures, as I said, you will have both spin and pseudo spin. So that's ln4. Okay, so you have 2 spin states, and accordingly you have 2 parity states as well. But then you go down in temperature, and below a certain temperature scale, you just end up with a free spin, and that's this green region over here. And then depending on the gate voltage, you can either end up with a 0 entropy state, which means that spin over there has already been quenched by these electrons in the leads, or you can end up with a state where the spin remains free. And that actually, I cannot go into the details, but that actually happens because how these parity states that I was talking about, these orbitals, how they couple to the leads. So in one case, one of the states couple antiferromagnetically, the other couples ferromagnetically, and that switching happens, and that's why you get a quantum phase transition. But that happens when you connect the leads in this way. So that's a symmetry dependent thing, because when you change the connection of the leads, you get a completely different physics. And now you see at this same gate voltage, what happens is the LN4 entropy does not go through any intermediate entropy change. It goes all the way down at 0 temperature to 0 entropy, which means that now you have an SU4 symmetric point. And by the way, these are rare occurrences, but we are already showing a simple molecule where you can get an emergent SU4 symmetry to occur just by tuning, the symmetry of the entire junction. So to summarize, I have not given you enough details, but I hope I have given you an idea about the formalism that we developed, with which we can deal with a lot more molecules. And we can create a database, hopefully. So that's one of the outlooks. And you can have both antiferromagnetic and ferromagnetic Kondo effect, depending on those J matrices, or depending on how the spins talk to each other, the spin on the molecule with the leads. And it's completely quantum physics with robust signatures, will happen below certain energy temperature scales. And the single device can, I'm just flashing it, can give you a whole lot of physics. And I have just given you just a glimpse of it. So, but you can get all of these things, and we have seen this to occur in this simple system. So with that, I'll conclude.
Thank you, Sudeshna, very much for sticking with time. So we have time for a couple of questions. If in case somebody is interested, please do raise your hands and go ahead and ask. Atin, please go ahead.
Hi, Sudeshna. Nice talk.
Hello.
So my question is that, hello, can you hear me? Yeah.
Yes, I can hear you. Yeah.
Hello, can you hear me?
Yeah, Atin, I can hear you.
Yeah.
So the question is that you talked about the Kondo effect. So what is the role of electrodes here? So you're assuming, I know in theory you're assuming any electrode, but are you assuming any type of S type of metal or S type of metal?
So
like gold or platinum, if you use, this will be different completely. So
so that's a good question. So right now what I have is a plain vanilla model. So I have no structure of the electrode present in my theory as well. But because so when I so let me just go to the slide since I have time. Okay, so when I told you this, right now I started from here. So I ignored this. I don't have means. I have plans, but I haven't done this part. So, that will probably be a collaboration. Through some collaboration, I'll do this. That's the idea. But right now I have started from here. So you can already imagine I have no structure of no information about the electrodes going in.
So your model basically takes into account, it's like a quantum dot, right? Molecule as a quantum dot.
Yes, you can think like that, quantum dot, but it's slightly more than that. So the electrodes are just this, okay, with some band structure, and right now it's some flat density of states. Okay, so that information in that sense has not gone in. That's one thing. And I would not say it's like a quantum dot, not purely like a quantum dot. You can think of it as energy levels, but you see, when I wrote this, I did not go through this slide, but in order to construct these J matrices, so the interaction exchange energies, these are matrices, by the way, that has the orbital structure, that has information about the symmetry of the isolated molecules wave functions.
One more thing, this vibration, like you have to, I think Kondo and vibration in these systems are very important. So
yes,
I think if you look at few papers from Urenthal's group from Weizmann, there is a Kondo and vibration. I think there is some work in Daniel's group before also.
Yes.
So condo and vibration are important. So are you also
Yes.
taking into vibration? Okay.
Yes.
Okay,
Yes,
that
so
will be
that's one of the ideas, one of the extension of this algorithm or formalism, whatever you say, would be to somehow incorporate the vibrations as well. But yeah, I mean, then this effective low energy models will also change slightly. But yes, of course, incorporate vibrations into it. That's very important, actually. You're right.
Okay, thank you. So just to inform you that we are also doing this kind of, we are doing experiment
Okay,
on
but
this.
I
So
cannot
it will
see
be
you,
good
so.
to okay, I'll send you an email. So that's
But anyway,
thanks.
yeah, you can write. Maybe you can write me an email. I would be interested to
Okay.
discuss more. And
Okay, thank you.
actually.
That I'll do. That I'll do. Thanks.
Okay, thank you very much. Yeah.
Yeah.
Okay. Thank you, Atin. So we are just at time, so I think we can stop here. So let us thank Sudeshna again for a wonderful talk. Thank you very much,
Okay.
Sudeshna.
So yeah.
And we can move on to the next speaker, which is Dr. Malay Bandyopadhyay. Malay,
yes. Can you hear me?
IIT, yes, we can. You are from IIT Bhubaneswar, isn't it?
Right, right.
Site says NISER.
Yeah, that's a mistake, I think.
Yes,
So I'm from IIT Bhubaneswar.
yes. So welcome, and Malay would be talking about environmental dependent vibrational heat transport in molecular junctions. So Malay, please go ahead and share your slide. And
yeah, can you see the
yes,
slide?
it's coming up.
Okay.
Could you just put it in the full screen mode and start? And I will give you a shout at exactly 20 minutes.
So is it in full screen mode now? Or,
okay, I can see your slide well, but
yeah, okay.
Okay, maybe you can start.
Yeah.
Yeah.
So first of all, I would like to thank the organizer for giving me opportunity to present this work on vibrational heat transport in molecular junctions. I will actually emphasize on the effect of environmental spectrum and quantum effects and vibrational mismatch on the vibrational heat transport in molecular junctions. Already in my previous talk, Sudeshna has already set the tone of why we are required this kind of studies. So I am not repeating those things. Like Sudeshna is basically talk about electron transport, but in my case, it is energy transport, and people are really interested because with the advent of molecular level technologies, the control over this energy transport at nanoscale is very important. That is well understood because in electronic application, we know that good thermal conductors are required because you require to efficiently remove excess heat generated by this electronic heat dissipation. On the other hand, in good thermoelectric devices, we require poor conductors. So that is one aspect. Besides that, so like intramolecular and intermolecular vibrational energy transport are important to understand the reaction dynamics in chemistry, mainly to understand the reaction rates. So in that sense, these kind of studies are important. In the slide itself, I have put 3 pictures, like to give you some idea about the what kind of systems we are dealing with in this kind of study. So in the left-hand side, I have given this one setup, typical setup where a alkene chain is sandwiched between 2 solid. Here one is like gold, and here it is quartz. And the end one is functionalized in the sense that so that bonding can be stronger. So this is one setup, and people heated this part and then try to calculate that how much heat current can flow through this molecular chain. And similarly, in the right-hand side, this is something like a alkene chain is connected with 2 big subgroups. These big subgroups is actually this azulene and anthracene. They are behaving like two heat reservoirs kind of thing. So one can shine some laser on this azulene and heat this one, and then one can measure that how much heat is transporting, like by measuring the loss of energy rate or by gain of energy by this anthracene. And this one in the middle, this is a typical model which will involve like this left and right are physical reservoir, and in between we have a alkane chain. So this is the typical setup which we will deal with. Now, why we are interested? Because there are many challenges in this kind of problem. Because first of all, this is a open system, open quantum system, and quantum effect is very much important because these vibrational modes are like much higher than the thermal energy. So quantum effects are very much important in this case. Also, these many body effects and this, you can see that there are multiple reservoirs are involved in this type of problem. Of course, it is driven out of equilibrium. So people are interested in this sense that from you have a fundamental point of view. Also, one can utilize this kind of study to study some kind of function or device making things. So from the fundamental point of view, the questions one can ask are like what kind of whether this transport is in the ballistic regime or in the diffusive regime, what are the signatures of quantum effects, what are the signature of many body effect in this kind of transport. So those are the particular things which are people are interested in this kind of study. Similarly, in the quantum thermodynamics, people are interested in the heat, work, and efficiency to find the heat, work, and efficiency of such kind of systems. On the other hand, in the functionality of such kind of systems is like you can use it as a diode, transistor, or thermoelectric devices. So in the present talk, I will actually discuss about one of the function of such system, like it can act as a rectifier. And to bridge between these two, you require some method development. So in that sense, we also involved in the development of a method to study, to handle such kind of challenging system, which is involved with, which is open quantum system, open non-equilibrium quantum system involved with many body effects and multiple reservoir. So in the present context, we find that self-consistent reservoir model is very much efficient to include all these points. So this self-consistent reservoir model actually introduced long back, like this Bolstrelli, Reed, and Vischer. They have introduced in 1975. Particularly, they have introduced this model in the classical limit. Then they have further modified it in the quantum limit, but weak coupling limit. Then Abhishek Dhar and Dibyendu, they have go beyond this weak coupling limit, but their studies are mainly in the linear response regime. Then we actually go beyond the linear response regime. One can also find a very good review on this subject by Vijay Agarwal and Veera Segal. And recently, Segal group has done a nice work on quantum effect of vibrational mismatch in such system. And these three are like some of the experimental work. So these are which I find that is important for the present talk. So there are many such kind of studies, but these references which I find that important for my talk. So I have included all of them, and here is the my objective. I will show that how this kind of heat current are affected by the chain length, then phonon scattering rate, and temperature gradient. Also, I will study the vibrational mismatch, how they affect this kind of heat current in the molecular junction. So this is a typical model which we are involved. You have a chain of atoms which are connected linearly with harmonic interaction. They are harmonically connected with each other. And these two, this T1 and T5, they are like physical reservoir. And the intermediate atoms, so this T1 and T5 are boundary, they set the boundary condition, you can say. But this intermediate reservoir, this T2, T3, and T4, which are connected with this second, third, and fourth atom, they are like phenomenologically, we are introducing this many body interaction and phonon-phonon interaction, etc., scattering mechanism phenomenologically by including this self-consistent reservoir. So in this case, we will set that this leakage current in the steady state is negligibly or vanishingly small. So we'll self-consistently determine this T2, T3, and T4 by demanding that this either this F2, F3, and F4 are 0. So by imposing that condition, we self-consistently determine this temperature profile of this intermediate reservoir, and then we'll find what other characteristics we can find. So this is the kind of self-consistent reservoir model. And then this is the model Hamiltonian. You can see that it consists of 3 parts. The system part, HS, this HL and HR, like this 2 physical reservoir which we can think of. And these HLS and HRS are like the interaction between the system and the left reservoir and system and the right reservoir. And these HI like intermediate reservoir, and this HIS is the interaction between the intermediate reservoir and the system. So these are like, you can easily see that all are harmonic in nature, so you can, and they follow usual, this X and P follows usual commutation rules, and you can use Heisenberg equation motion. You can solve them, and you can actually use, you can obtain a generalized Langevin equation of this system, where this dynamical friction kernel, which can we model with an exponential cutoff, and this parameter R with 3 different resin, we can identify it as the ohmic environment, sub-ohmic environment, and super-ohmic environment. And by finding the position momentum correlation function, one can actually obtain this heat current in the system, where G omega is the phonon-Green's function with a tridiagonal matrix with the respective elements, like off-diagonal elements is this, and the diagonal elements with this form. So with this, now you cannot get the exact analytical solution of this equation 5. But in 2 limiting conditions, you can get the exact expression. Like in the quantum linear response regime, you can obtain the exact expression. Also in the classical domain, you can get that. But to go beyond that, you as I said, you require to solve this nonlinear equation like this equation 8 for n-2 number of, you will get n-2 number of such nonlinear equation. You are required to solve this nonlinear equation numerically. For that purpose, we use Newton-Raphson method to solve this one, and we can update this temperature profile using this equation 11, where D inverse is the Jacobian matrix with such elements, where Fi we have this function already. So we have a OLBF function. We are interested to find the solution of this equation, and after getting the solution, we can by iteratively process and we can get a converged value of this temperature. So we need to verify whether we have achieved correct convergence. For that purpose, we consider three quantities like heat current. It should focalize to a certain value after a few number of iterations, and you can see that they really converge to a certain values for like after of the order of 10 to the power 2 iterations, they converge to a certain values. Then we need like this intermediate temperature of this reservoir should so this temperature of this intermediate reservoir should converge to a values which is in between this temperature of T1 and T5. So you can check that we actually consider T1 as 0.5 and T5 as 0.25. So this T4 is actually converged to a intermediate values. And then we said that, as I said, that this leakage current should be vanishingly small. So after convincing all these things, we are convinced that we are getting the correct results for this self-consistent reservoir model. Then we go to the study of thermal rectification. And for that purpose, we consider two different kind of systems. One is such kind of system where this right-hand part is we introduce, you can think of some defective part, where we introduce some defects in the single wall carbon nanotube, and the left-hand part, it is pristine part. So the model is like, since you have introduced some defects here, so you have less number of sp2 bonds, so less number of interaction is there. So that's why you will have a less interaction strength. So that's why we said K as less than 1, and we said that left hand part as K equal to 1. So in that way, this is the model. You can think of the spring graded chain, where this left hand part we set a certain values of K, which is larger than the right hand part. And with that, you can obtain the rectification, where rectification is defined in this equation 12, where J plus is the current when T1 is greater than Tn, and J minus is the reverse one, when you reverse the temperature bias. So we have obtained almost like for the super ohmic case, we get a higher amount of rectification. And this can be explained from this temperature profile, because for the super ohmic temperature profile, this asymmetry is large. So that is actually explained why we get the large amount of rectification in the super ohmic case. And similarly, another experiment was done by Chang et al. They actually inhomogeneously loaded this carbon and boron nitrate nanotube. So we model this one in this form, like we have include this mass graded system, like we increase the mass in this fashion, equation following this equation 13. And again, one can show this rectification property of such system. And again, you can explain the things like in this case, ohmic case is giving you the highest rectification, and this temperature profile can explain this one.
Malay, 5 minutes more.
Okay. So then we can discuss about the length dependence. You can see that this anharmonic effect here, so that including that anharmonic effect using this self-consistent reservoir model, you can see that current is decreasing with the length. As you increase the length, you can see that current is decreasing. And from the log plot, you can actually get the scaling of this decay. And in the for a long chain, we try to like how this decay occurs. So for the what we find that for sub-ohmic case, this decay is you can achieve the Fourier's law compared to for a shorter chain than the others too. So you can actually check whether Fourier's law can be achieved or not, but for using this thing, but for the computational limitation, we cannot go beyond this this 30 number of atoms. So here we find that this slope is like 0.75. So if you take a higher number of atoms, you will definitely achieve this Fourier's law. Then this scattering rate dependence, we have seen that as you increase the scattering rate, this decay, you can find that this recombination and splitting of phonons occurs. So you can naturally increases the thermal resistance to the heat current. Okay, so this is an important observation. What you can see that when we have a scattering rate which is independent of temperature, then we are actually missing some phenomena which is observed in the real system. In the real system, you can see such kind of turnover behavior, like initially the current increases and then it decreases. So to incorporate that, we actually include a temperature dependence scattering rate, and including that, we can observe that initially this current increases and then it decreases. So that one, and the other things which we want to show that phonon mismatch effect. So this one is actually experimentally observed by Majumdar et al. Here. This is self-assembling nanolayer of alkane chains, which is sandwiched between different solids. So they have shown that as this phonon mismatch increases, this conductance decreases. And we also show the same kind of behavior here. The extra aspect which we observed that here, that dual role of this self-consistent reservoir. So in this regime, the self-consistent reservoir actually helping to overcome this phonon mismatch thing. So that initially it increases, and then when this after you achieve, you go beyond certain scattering rate, which is of the order of the typical frequency of that system. So beyond that, you will see that that decreases naturally. So that's so another two things which we observed, that phonon up conversion process, where you set this right hand side that Debye frequency at certain value, and you start the hot bath with the frequency, Debye frequency is same as this cold bath, and then decreases. And you can see the effect here. that as you mismatch increases, that current decreases. The same thing happens for the phonon up, phonon down conversion process. So with that, we can conclude that we have investigated thermal rectification in two systems. One is spring graded system, one is mass graded system, other one is mass graded system. We also just showed that different effect of chain length, scattering rate, and temperature on this kind of heat current in molecular junction. And we also exhibit different environmental effect, like how this ohmic, subohmic, and superohmic bath affect this kind of system. We also try qualitatively observe the turnover phenomena which people have observed experimental. So with that, I would like to thank all of you for your attention.
Thank you very much, Malay, for sticking exactly to time as well. So we have a few minutes. If there are a couple of questions, we can accommodate that. So anybody who has questions can please raise your hands on the Zoom and go ahead and ask. No questions yet. So Malay, can I ask you something? You used your mass graded model to try and replicate results of these inhomogeneously loaded nanotube structures, isn't it?
Right.
But in inhomogeneously loaded nanotube structures, the mass would not be graded. I mean, it will be inhomogeneous. It will be probably even random, isn't it? But so how accurately would your model be?
In the model we tried to model like that. So in the experimental scenario, it will not follow such kind of uniform kind of increase or something like that.
Do you think it will change something dramatically in your models? If you,
but it actually shows the correct nature of that tendency. Like with that kind of, you can say crude modeling. Also, we be able to capture the general nature of that tendency. Like the direction of rectification is same as that which observed by that experimentalist. And basically the previously some molecular dynamics simulation, they failed to capture that one. I don't know why, but their direction was opposite to this, the observed thing. So this is like what we can say that the self-consistent reservoir model is better than that way.
Okay. And another quick query regarding the rectification numbers itself. I mean, what is it? I mean, they're not remarkably high. I mean, even in
in the experimental things also, that is not remarkably high. That's
really
why so that's why like this thermal rectifier are not like people are working on that. Like this Chang et al, they have seen at most like what I can remember 10% rectification. That's the thing they have observed.
Nice. Okay. Thank you very much, Malay. So I do not see any questions being raised. So then let us take this opportunity to thank Malay for his talk. Thank you very much, Malay.
Thank you.
And we can move on to the next speaker, which is a contributory talk from Atanu Jana from NISER. Atanu, can you please, Malay, can you unshare your
screen? Yeah, sure.
Thank you. So Atanu, could you please go ahead and share your talk?
Yeah. Is it visible?
Yeah, I can see your screen, not your open PDF yet.
No, no, no. Oh.
Atanu, could you please stop sharing and then share your entire screen?
Oh.
Maybe that will help.
Yeah, that's better.
You put it in presentation mode. Thank you.
Yeah.
Yeah, please go ahead, and I'll give you a shout after 10 minutes.
Okay.
Thank you.
Okay. Hello, everybody. I would like to thank the organizer for giving me a chance to present my work at the conference. So, topic of my presentation is single particle Green's functions across the many-body localization transition. This work has been done under the supervision of Dr. B. Ravichandra and Dr. Arti Garg. So, this is my brief outline of my talk. So, I will talk about that model and method which I have used for all of the entire study, and I will also discuss about that different kind of averaging, mainly typical averaging and arithmetic averaging of local density of states and scattering rates. I will briefly touch upon that many body localization transition and many body mobility edges. So we know, starting from the non-interacting system, introduction of interaction and disorder individually can lead to different kind of insulator, namely Mott insulator and Anderson insulator, which are different from band insulator. But the combined effect of interaction and disorder is an active field of research because it can lead to the many-body localization, which has some interesting properties like all the eigenstates are localized, and it shows that a lack of transport up to a finite temperature. So there are many tools that can detect that many body localization transition, mainly gap ratio statistics, entanglement entropy, and statistics of eigenfunctions. But in our study, we used single particle Green's function to capture the MBL transition. So one of the typical schematic of MBL phase, which looks like that, obtained by Lewis and other group. So one can see that for low enough disorder strength, all the eigenstates are ergodic and extended, and the states at the edges starts to localize when the disorder strength is increased. At a very higher disorder strength, all the eigenstates are localized. So some of the usual tools that can detect MBL are gap ratio statistics, entanglement entropy, and statistics of eigenstates, but they are not easily experimentally measurable. So we used single particle Green's function that can be easily measurable. However, earlier work which treated interaction and disorder together mainly treated the interaction perturbatively, and their main focus was on the properties of Green's function in the thermodynamic limit. But in the earlier slide, we have seen that MBL involves many higher excited states. So that cannot be captured well. So in our study, we used disorder and interaction exactly, and using exact diagonalization technique, we calculated that single particle Green's function for all the eigenstates of a finite system size. So we take a half-fill system of spinless fermion with nearest neighbor hopping, nearest neighbor interaction, and on-site random disorder. So T is our hopping parameter and V is interaction strength. We fixed both V and T to equal to 1, and we took that random disorder is distributed uniformly in the range of minus W to W. So using exact diagonalization, we calculated that single particle Green's function quantities for all the eigenstates starting from the system size 12 to 18. So we use that prescription to calculate the Green's function. Here psi is the nth eigenstate of the many-body Hamiltonian. From the Green's function, we obtain the local density of states, and we generalize that Dyson equation to get the self-energy for nth eigenstate, and from self-energy, we get that scattering rates. So as we are dealing with some disordered quantity, so we have to define disorder average of local density of state and scattering rate. That geometrical averaging is that local density of states is as usual geometrical averaging, and that average is that usual arithmetic averaging. So we also did same averaging for scattering rate and scattering rate. Here C is the number of disorder configuration and L is the length of the system. So we rescaled our energy in the range of 0 to 1. So we follow as that to rescale that energy. Here N is the energy of nth eigenstate and Gs is the energy of our ground state. And we focused on that low energy excitation behavior of the mid-band states. We take that our eigenenergy is in the range of 0.495 to 0.505. So in study of the MBL phase, one of the common tools is that level spacing statistics, where delta in is that the energy difference between two consecutive eigenenergies, and from there we obtain that level spacing gap ratio. In the left hand plot, I plotted that mean value of gap ratio for different system size. So one can see that for very weak disorder strength, that gap ratio approaches to Wagner distribution, and for very strong disorder strength, it approaches to Poissonian limit, and roughly that crossing point of different system sizes indicates that transition from ergodic to non-ergodic phases. So in the second and third panel plot, we plotted the ratio of typical local density of states and average local density of states at omega equal to 0. And in third panel plot, we plotted the ratio of typical scattering rate and average scattering rate at omega equal to 0. So it's clear that for very weak disorder strength, that ratio is of the order of 1, and it increases with the system sizes. But whenever we increase the disorder strength, it starts to decreases, and for very weak disorder, for very strong disorder strength, it approaches to a vanishingly small number. And at some disorder strength, that ratio become independent of the system sizes. We define that is that MBL transition point, and that ergodic to non-ergodic transition point obtained from the level spacing statistics qualitatively matches with our ratio of typical to average, where that ratio become independent of the length. Earlier, for non-interacting cases, earlier people studied the distribution of local density of states. So they found that near the transition points, it behaves like log normal distribution. That also motivates us to show the distribution of local density of states and scattering rate for the mid-band state. We found that for very weak disorder strengths, that distribution is like broad distribution, and that typical value and average values are close to each other. And for very strong disorder strength, that most of the weight shifted towards the zero, and that typical values and the average values are far from each other. So in our cases, that that distribution is also fitted quite well with log normal distribution. So the catch of this study is that whenever we increase the disorder strength, the typical value approaches to zero faster than the average value approaches to zero. So earlier I have shown you only that result of mid-band spectra, but we calculated that Green's function quantities throughout the spectrum, and we compared it to the gap ratio statistics. So one can see that that for very weak disorder strength, that gap ratio, mean gap ratio values approaches to the Wagner distribution values, and for very strong disorder strength, it approaches to Poissonian value. And in the intermediate disorder strength, there is a crossing of different system size that roughly estimate the many body mobility edges. So in the right hand plot, I plotted that distribution of that scattering rates, I mean the ratio of typical scattering rates and the average scattering rates. So it is clear that values are smaller at the edges, and it increases in the middle of the spectrum. And for very weak disorder strength, that ratio is of the order of 1, and for very strong disorder strength, that ratio is vanishingly small. And in the intermediate disorder strength, up to a particular energy value, different system sizes approaches to a particular value. So we can tell that that particular energy is roughly that many body mobility edges. So many body mobility edges obtained from the gap ratio statistics and Green's function are qualitatively consistent with each other.
Atanu, can you wrap up in a minute or two?
Yeah.
Okay, thank you.
So primarily we focused on low excitation behavior of our many body eigenstates, which indicates that gamma omega equal to 0. But here we have examined that behavior across all finite omega, and we find out that for higher enough disorder strength, typical value of local density of states and scattering rates become vanishingly small for all omega. And here I am showing you that ensemble average of that quantities throughout the all spectrum. So that behavior also mimic the behavior of the midband data. So in summary, that single particle Green's function quantities can be used to locate the ambient transition points. Transition points calculated from Green's function consistent with gap ratio statistics. In the delocalized phase, both the scattering rates and local density of states have broad log-normal function-like distribution. Many-body mobility edges obtained from gap ratio statistics and Green's functions are qualitatively consistent with each other. And thank you for your kind attention.
Thank you very much, Atanu, for sticking exactly with time. So maybe there is time for a quick question also. If in case somebody has any questions, please feel free to raise your hand on Zoom and go ahead and ask.
Hi, Atanu.
Yeah.
So I have a simple question. So when you, in one of the slides, you showed finite omega typical density of states, or yeah. So what do you mean by finite omega? Is this you mean the omega dependent? This is what.
Yeah, omega dependent.
Or so it's not very clear to me how you relate this density of states or the gamma typical whatever with the many body localization. Can you just give me an comment on that a little bit?
So I mean, earlier we fixed that our omega equal to 0 and we obtained that midband data. So now we calculated that Green's function throughout that omega range, and we choose that our state's energy is near to that 0.5 in the rescaled energy scale, and we from that single particle Green's function we obtained that local density of states and
so you mean you extract the value at E equals to 0.5 from your rho typical, is that right?
Yeah, I mean that energy of that eigenstate is 0.5 in the rescaled, I mean in the rescaled energy scale. So your energy lies between 0 to 1. So that energy of for which we calculated these quantities are near to 0.5.
Okay, and okay, I got it. Yeah, and just one more comment. So in the initial slides, when you mentioned the papers by Volhard Group and Eugene Semler. So maybe it would be nice if you can add a few more papers over there. So I also have a few papers, and we can also chat over if you want. We can also discuss. So yeah, there are some other papers that we have done where we had, it's not perturbatively looking into the single particle Green's function. Just to give you an idea about, you can go through that in the literature. So you can search with my name. Okay.
Yeah. I think it's a 2016 paper.
2016, yes. 2016, 2018, yes.
Yeah.
Okay.
Thank you, Sudeshna. So we come to the close of the session then. So a big thanks to all the speakers for sticking with their stipulated time slots. Thank you very much then. And the next session, I believe, starts at 2:30.
Yeah, so thanks also to the chair of the session, Professor Sunil Nair. So we'll meet again at 2:30.